Yes.
So we will use again the idea of differential form in chapter 2. But in chapter 2, I try to give you notes for the dimensionless parameter. Okay. So previously, I think in your undergraduate study, your lecturer maybe discussed about the Buckingham Pi theorem. Is that familiar with you, terms of Buckingham Pi theorem?
Yes, Professor.
Okay, so I think you have
No,
idea
no,
about
no. To
what?
me, no, sir. No, to me, sir.
Okay,
Yes.
okay. So you just focus to this notes. Okay, so the idea of Buckingham Pi theorem is we need to the way how we produce the dimensionless parameter, because it is not just a try and error. For previous researcher comes out with Reynolds number equal rho VD over mu, and then we have the Mach number which is V over C. We have the Freud number. We have everything. So it is not just coincidence. Actually, there is one scientific method to be conduct before we could announce or we could get dimensionless parameter for each situation. And this dimensionless parameter is actually referred to uh, parameter that we have in our research. And okay, but what I would like to show here is I would like to share you the method for how to get the dimensionless parameter in differential form. Because in normally in an undergraduate study, you will learn the Buckingham Pi theorem to derive or to get the dimensionless parameter for the exact parameter. Means they will give you pressure, velocity, diameter, and so on and so forth. But we have a little bit different method to do the dimensionless parameter in differential form. Okay, so this is the note. So dimensionless parameter in viscous flow. So since our basic equation of motion are extremely difficult to analyze in general, we should cast them in their most efficient form, thereby increasing the usefulness of whatever solution we find. This accomplished by non-dimensionalizing the equation and boundary conditions. For simplicity, assume constant Cp and Cv approximately true for all gases, and also neglect the second coefficient of viscosity, lambda, which is seldom needed. Then one then our four variable P, rho, V, and T will depend upon space and time and 8 parameters that occur in the basic equation and boundary condition. So the idea of this statement is actually because sometimes in dimensionless parameter, so they are a very specific parameter, or they have a parameter that only use seldom on. Okay, so to simplify this one, so we make all of this assumption. So and then the idea is uh, we need to have the three basic groups. Okay, so I read this first. So above mentioned parameters are assumed to be known from data or thermodynamic state relation. Gravity is constant. We need to select constant reference properties appropriate to the flow. So this is a three reference. So the reference is actually about the velocity, about the length, and about the properties. So I will discuss about it later. So and then a steady viscous flow have no characteristic time of their own. So select particle resident time L over U as a reference time. If the flow oscillates with frequency omega, one might select omega 1 over omega as a reference time. Okay, so first, so what is this reference show? Is actually they try to pick up the major parameter that influence the flow. So first, is for sure the velocity. So, okay, in certain textbook, they will call this one as the kinematic parameter, mean parameter that's telling you about the velocity of fluid or the motion of that object. Okay, so that's one here. Sometimes we need to take the omega, the rotational speed, instead of the linear speed, because usually we will take the value of linear velocity of that fluid, not the rotational speed of that circular object, for example. Okay, and then the L here is to reflect the geometrical parameter, means the whether that object is big or small, if or whether it is with the volume, the area, and so on and so forth. But okay, because the dimensionless parameter is actually to get a very basic equation, mean a very basic dimensionless equation. So normally people will take very basic property dimension properties as geometrical properties. Okay, that's why in normal dimensionless parameter, you will get the geometrical properties, whether it is length or diameter or radius. Okay, it is very rare. I think it is not exist any dimensionless parameter who take area, for example, and A, or take a volume in its dimensionless parameter. It is because A actually it will consist of width and length, width and its length. So if the A increase, you might don't know which length is increased, whether it width or whether it length, or both of them are changed. So that is the one disadvantage if you take secondary parameters like surface area, like volume. So because it consists of another equation, so means that before you could know which parameter can affected the situation, you need to know uh, the 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 parameter that change that one first. Okay, that's why people will take the simple geometrical parameter. And here, free stream properties here, it will reflect the dynamic parameter. So dynamic parameter is actually the the parameter that has relation with others. They will take something that will influence the object. Okay, okay. Normally, okay, in some textbook they simplify the idea is, okay, if you want to take the length here, the length must be one single unit, which is meter, or we will use the MLT system, so it will refer as L, which is the length. Okay, and then the U here is the kinematic. Kinematic means you are dealing with meter per second. It need to show the velocity of that fluid, or in MLT system it will become L over T. So it will repeat the speed, actually, the velocity. And then the free stream properties here, they will reflect the dynamic. Okay, the dynamic is actually everything that involve mass. Okay, so the symbol is M is actually the mass here. So means the unit is, so the unit is actually the kilogram. Okay, so that's why if you see here, okay, most of the properties for the free stream properties is the density or the pressure. Okay, normally in fluid they will use density as main pressure instead of dynamic viscosity. Here we have mu here. Okay, normally they will take density as the major properties for the dynamic parameter. Okay. Okay, however, for the differential value, for the differential form, okay, we need to understand a little bit for the way how the dimensionless parameter being conduct. So the idea is we will use the idea by asterisk. So we put, for example, if we want to evaluate the x, okay, so we put x star here, and it is equal to x over L. So normally x will show us about the length. So and then we put it and we divide by the common length. So we could get the changes. So this is the meaning. So and then we have time is time over U over L. Okay. So U is velocity. If you check the dimension here, U is meter per second. So and then meter per second, the second will cancel the T here, and the meter from the U will be cancelled with the length here. So we have the T star is equal to U over L, and also the pressure here and the value of phi. So we are not using the phi, so we have the rho star here. So means we have the rho star means the common the current exist density divided by its reference value. So this is the changes of density and so on and so forth. So normally this one is already fixed, or it need to determine from the situation of our from the observation from the experimental setup. Okay, to make sure that we reflect the real situation. But in your test or in your final exam, I will give you the table of this one. So you just use pick up this parameter. Okay. So and then we try to make calculation of dimensionless parameter with our continuity equation and also our Navier-Stokes equation. So for example, this is the continuity equation that we learned previously. So the idea is mass can be written as rho times volume. So and it must be constant. So we write dm over dt, and then we substitute the m. We have a d over dt rho volume, and then we can write as this one because this is the idea of a differential form. So and then we have rho d volume dt plus volume d rho dt, and then we could get this one the relation between normal strain rate as this one, and then we could substitute everything. Then we could have the idea of continuity of this one. So and then for incompressible flow, so the del or the nabla of v here is equal to 0, because as you know, the for incompressible flow, so the value of density is not the density is constant. So finally we could get this one, a1 equal a1 v1 equal a2 v2. Okay, that's the common continuity equation. And okay, so we take that continuity equation. So and then this is the what we have just now, d rho over dt plus nabla rho v. So and then this is the dimensionless variable, as I said previously. So this is the table. So what we need to do is we substitute the value here. So for example, we have the rho here, del rho, we have the rho here. So we substitute with this term. Okay, and then what we need to do is we need to substitute the value of rho with rho star times rho naught. Okay, and then T here with the T star L over U, and okay, and volume here is the volume star time U, so it's become, we could take this one. Okay. So we substitute everything here. So, and then if you get this one, so we take, we could take out, we could cancel the value of rho naught U over L, both here, we could factor it, and then we could equal it equal to 0. So, and then the equation left is like this. Then if you compare this equation with the previous, with this equation, you will find that it is uh, it is totally the same. Okay, okay, unless the star here, only the star here is exist, so all the term is actually will is actually same with the previous equation. So we assume that there are no dimensionless parameter could be produced. That's why if you look back into my first notes about the dimensionless parameter, we have a lot of common parameter can be used in flow in pipe, in open channel, in for example in Mach number for the compressible flow and so on and so forth, but none of them is actually can be used for evaluating the flow rate. Okay, because the flow rate is actually the parameter in the flow rate is actually not enough to create the enough to create the dimensionless parameter. That's why it means that by there are no dimensionless parameter can be produced. Okay, then we go for our Navier-Stokes equation. So this is the Navier-Stokes equation, the simple one. So we could substitute the value of rho star, and we have the rho star here because we have rho and g is constant. So we have velocity v, we have time here, okay, and then we have mu, okay. We have p pressure here, and we have nabla here. So and nabla, this is the one. And then we substitute all the value here with in equation number 1. So I think you could do this all, and then so the g is constant, so you put everything is here, okay, and then the nabla is also can be substitute by this one, mu, okay. So nabla, okay, nabla is equal to L nabla here. Okay, so you could substitute this, and then you could rearrange this one. Okay, and then you could factorize it like this one. And then you divide it all with rho naught u square over L, and finally you will have this number. You will have this term. And then if you compare this term, you will find that it is not 100% equal to this one. For example, we have a rho g here, but for this one, we have, okay, because we neglect the value of rho with g here. Okay, so we have a rho and g here. Okay, this is still rho g, but we have an extra term which is L and L over u square. And also for this one, we have mu, rho, u, and L for this term. So now we could change the idea of this one. We could take this one from, if you compare with our previous notes about the dimensionless parameter, so GL over U square is actually a Freud number. And as you know that rho UL over mu is the Reynolds number. So in this situation, it will become 1 over Reynolds number. So from this evaluation, we found that for Navier-Stokes equation means when we have fluid flow at any condition, there are two dimensionless number that can be used to solve this situation. So one is Freud number and one is Reynolds number. However, in the specific after in a specific condition, Reynolds number, it might be used for flow in pipe, but Froude number is actually used for open channel. Open channel means a fluid flow which has a free surface, mean a part of the fluid is contacted with atmospheric pressure, like a river or like an open conduit and so on and so forth. Okay, this is the way we prove the dimensionless parameter from the differential form. So and then again, if we do the solution for 2D Navier-Stokes, that one, okay, so we just use this one for example, and this is all the dimensionless parameter. And if you substitute all of this, okay, here the the difference from this equation is we take care about the we let the nabla here stay on its dimensionless form, but for the next calculation here, so we have a Navier-Stokes which has the specific term, so we don't have any nabla anymore, so we have del square u over del x square and so on and so forth. So here, I would like to show you how to do the dimensionless calculation if you have quadratic terms, the power of 2 here. Okay, so first, it is easy for us to have to solve the du dx, du dy because we already have the u and y here. Okay, so and then we could substitute the value only. But if you need to substitute to substitute the value of del square u over del y square, so we need to do the calculation like this. Okay, so for example, for du dx, so we just substitute the value of u here, and we substitute the value of x in terms of dimensionless parameter, and then we could have this one. And this is for du dx, and this is also for du dy. And dp dx is also can be done by substitute the value, and you will get this one. Okay, now you could see that we have a del u star, del x star, and so on and so forth. Okay, but for this one, okay, if you do the mathematics, you could do it. So first, we substitute the value of del x for del u dx here. So du dx is already know from this calculation. So we substitute in this one. So and then what you need to do is we just give a dummy parameter. So means from here del over del x, we just write it as del over del x star times del x star over del x. Means that the value of del star here, del x star here can be neglected. So what we do is actually we try to rearrange this. We try to rearrange these terms. So we have the x star here, and then we bring the u star here, and then we bring the x star here, and we have u star. Dx is here. Okay. So and then we have an L here, and finally we could change it into this one. Okay, and then another note for this one, for example, we have del x star is equal x over L. So del over del x for the x star is equal del over x over L. So and then we could say it is equal to L because del x over del x, we assume it can be it's cancel each other. So we have 1 over L. So means now dx star over dx is equal to 1 over L, and dy star over dx is equal 1 over L2. So I think this is dy star over dy. Okay, so I hope by understanding this, okay, you could do the equation. So we substitute all the star parameter here. So in the left hand side, so we have this term, so we substitute everything. Now we have this one. So and then for the right hand side, so we have this term, so you put everything, so we have this term. And finally, we equal the left hand side with the right hand side. So we have this term, so you divide with RU square over L to simplify the term, so you will get this one. So and then we could say that again here we have a mu over rho UL. So this is the equal with the Reynolds number. We know that Reynolds number is rho UL over mu, and then the 1 over Reynolds will become mu over rho UL. So this is the way we determine what type of parameter or what dimensionless parameter that can be used or has possibility to be used in our fluid problems.